Hi, thanks for everyone for coming. Allow me to introduce myself a little bit. My name is Bola, and I'm a research fellow over in mechanical engineering department, and I'm based in the non-destructive evaluation group, short for NDE. And traditionally, the group works on a lot of projects with the nuclear, oil and gas, and aerospace industries. We specialize with ultrasound with related ND techniques that are used to detect defects in, for example, pipe structures, characterize material properties in aero engine materials, and so on. And about 2 years ago, we started collaborating with the batteries group in our department and researching on the NDE of lithium-ion batteries. So today I'm going to talk about two of the progresses that we've made recently, and it's all related with quantifying layer level properties of lithium-ion batteries. And in fact, we've discovered that ultrasound can contribute to the characterization of lithium-ion battery cells throughout their lifetimes, from manufacturing to in-service monitoring and to second life and recycling. So each of these stages, ultrasound can contribute in characterizing the list of properties that I've put here. But today I'm going to talk about two of these outlined in red characterizations. First one is to measure the tortuosity and the porosity of the porous electrode potentially during manufacturing process. And the second one is to monitor characterize the layer properties in service for a pouch cell. So the first one is about manufacturing and quantifying electrode tortuosity. So probably you know more about how the tortuosity is affecting the performances and properties of pouch cells. But basically, the electrodes, for example, anode and cathode, their coating layers are made of a lot of particles and matrices. And in order for the ion to go through the electrode material to reach the other electrode, it needs to go through the tortuous pathways through the particles, through the matrices, in order to perform the charging and discharging process. So tortuosity and porosity, therefore, are key determinants of the performances of lithium-ion batteries. But unfortunately, the popular quantification methods are relatively cumbersome. So you either need to construct a working battery cell in order to evaluate how efficiently the ions are passing through, or you need to take the electrode, cut it off, and put it into a micro CT scan and reconstruct the structure to mathematically calculate how large the tortuosity is. So interestingly, ultrasonic ultrasound can contribute in this because in porous materials, there are three different modes of wave propagation. So I think you should know that in solid, there are two modes of elastic waves propagating through. One is a compressional wave, which vibrates along the propagation direction, and the shear wave, which vibrates perpendicular to the propagation direction. But in porous materials, there are three modes. One is a fast compressional wave, which goes through the solid particles. And the shear waves also go through the solid particles. But the special one is the slow compressional wave, which only goes through the air that existing in the tortuous pathways, the same as the ion needs to go through. So by measuring the wave speed of this slow compressional wave, it's basically slower than comparing to the waves that go through directly into the same length. And the ratio between these two will give you the tortuosity of the porous material. So that's the fundamental physics why ultrasonics can be used to measure tortuosity. And actually, ideal experimental setup would be relatively simple. So if you have a transducer, so everything will be in air, and you can put two transducers on either side of the electrode, and by measuring the propagation, in terms of amplitude, in terms of speed, you can potentially measure the tortuosity and porosity for that matter, and feedback to the controlling system in real time, because this measurement only takes microseconds in the level of microseconds, and that can potentially provide real-time feedback of the quality of the electrodes you are measuring. And so that's our ideal vision on how this could be integrated into the production of electrode. But obviously, there are challenges facing us in order to achieve this vision. That's because of two properties of electrodes. One is the electrodes are normally extremely thin compared to what the length scales we normally work for. Imagine if you have a relatively thick layer of pure, porous material. In fact, it's actually relatively well established for like foams, sandstones, and so on. In order to measure their tortuosity, you simply put two transducers on either side, and the slow mode will separate in the signal in time domain, because they travel at different speeds with the faster wave. But for electrodes, because they're extremely thin, then the propagated wave would overlap, even though they are slower. But because the traveling distance is too thin, then these signals will overlap with the faster wave. And also, the electrodes are made of a metal core in the center with the coatings on either side. So that's a multi-layer system compared to a single porous slab. So that's the technical challenge we need to overcome in order to achieve the vision, real-time control feedback of the electrodes that I mentioned earlier. So our first step towards overcoming this is to establish a robust theoretical model to predict the wave propagation. So these are probably a little bit complicated, but the basic idea is that we need to account for each layer, either it's porous, or whether it's a solid, or whether it's air, and we need to account for at the boundaries the compatibility and the equilibrium in order to in order to properly model how the wave goes through each layer, and then we assemble these wave propagations at each layer together into a matrix, so that we can model how the wave would go through the multi-layer system in any propagation direction, as well as in any frequency component that you put into the signal. So the purpose of these slides and the next are just to show the fundamental physics behind it. Is actually quite complicated in terms of like equations, but that's our expertise that we can bring to this problem, and we've actually done it. So the theories have been established, and it's working now. So the next is to experimentally validate our solution of forward predicting how the wave propagation is happening inside of a multi-layer system. And we've established a experimental platform like this. So you have two air-coupled transducers. As I mentioned, it's relatively simple. You have two transducers aligned, and you have a layer in the middle, and we have a rotary stage that can rotate the layer in relation to the wave propagation direction. So we can measure the time trace and calculate the amplitude as well as the travel time. So for the validation sake, we firstly focus on the propagation amplitude in this case. So that's reflected by a transmission coefficient. So in this figure, the horizontal axis is a wave frequency. So we can change the wave frequency in the theory, and we can validate it by using different frequency transducers. And on the vertical axis, it's incident angle. So we can so that's a result of rotating the sample in relation to the wave propagation direction. And the color in this figure shows the transmission coefficient. So as you can see, there is a very strong transmission at a particular curve along different frequencies at different angles. So if we do a cut of this at different frequencies, and we can see that at particular frequency, at particular incident angles, you have near 100% transmission in this particular angles. That's because those would correspond to particular wave modes through a single layer of solid, and that would facilitate the propagation through the layer. But other than these angles, the other directions, they have very little energy that's going through the layer. And we can do a section on the frequency, on the horizontal one. And so at a particular transmission angle, if we change the frequency, then we can also see a very special frequency component that's going through the layer. So that's for a single solid layer. And we can do that for a single porous layer as well. So we can do a horizontal cut, which gives you a frequency dependence at a particular incident angle. And in these curves, the predicted one are the curves, and the experimental ones are the dots. So that again reinforces our model is actually working for both solids as well as a pure single porous layer. And we can then do the combination of the three, and we have a porous solid porous anode. In this case, it's 500 microns coating layer thickness, and the porosity and tortuosities were measured beforehand, so that we can predict how the air coupled ultrasound is propagating through it. And in this case, at the common frequency range of up to 2 megahertz, sorry, and you don't actually see much changes up to here. Well, our theory is still working, so the predicted angle dependence and as well as frequency dependence are also agreeing with experimentally measured transmission. But there isn't much going on inside of this angular frequency range. But if we go up a little bit, then there are features that coming up. So the higher frequencies will give you a little more features in terms of how the sensitivity and tortuosity is affecting the wave propagation. And in fact, if we focus on these higher frequency components, and if we change a little bit on the tortuosity value, you can see the sensitivity of these amplitude response of the through transmission is coming up. So these are proving that the wave propagation is indeed sensitive to the underlying properties of the coating layers in terms of tortuosity and potentially porosity. But so far, we've only done the forward prediction. So we've established a relatively complicated theoretical model to predict how the wave is propagating through the multi-layer system. So that's our first step. We have a temperature warning. I don't know what that is. Okay. And the next step, obviously, is to use this forward prediction model in order to investigate how the sensitivity of the changing properties of the electrode layers is affecting wave behaviors. And we will then find out the high sensitivity configurations, and then attempt the inversion, model-based inversion of tortuosity as well as porosity for the characterization of these properties. So in addition to the characterization of the dry electrodes, we've recognized that ultrasound can potentially characterize even more manufacturing processes. And for example, the formation of slurries, actually, ultrasound is an established method of detecting the viscosity of slurries and also the particle size as well as density. So we can use ultrasound to bulk wave ultrasound, which is easier to work with compared to air-coupled ultrasound. And we can characterize the formation process as well as the quality control of slurries. And since we are developing, and if we succeed in developing porous electrodes, and we can do the end of the, so we can do either end, first on the slurries and then on the porous electrodes, we can do in the middle of the drying process as well. So how the slurry coated on the metal layers are drying towards the and end up as porous electrodes. So that will have a physically that will be a very interesting process because slurries and porous structures are completely different materials in terms of ultrasound, and their behaviors will be completely different from physical side. So it would be interesting to see how ultrasound would behave in the drying process as well. So yeah, so that's my first bit of talk on how ultrasound could potentially contribute to the manufacturing of electrodes and battery cells. The second one is about in-situ ultrasonic characterizations of battery cells. And as we know, batteries need improvements over safety and performances, and ultrasound could potentially bring advancements to the characterization properties over the traditional electrical motor-based methods as well as X-ray tomography, because they are simple, cheaper, and more available in terms of integration into in operandi operations. So typically, ultrasonic setup in literature is just to put an ultrasonic pulsar onto a battery and do through transmission. But what we are showing in the following slides will be a more advanced ultrasonic characterization capability, which is to identify the layer, each layer property inside of battery. So I think everyone in this room is very familiar with a pouch cell, the typical setup, structural setup of a pouch cell. And you have these anodes and cathode structures repeating for a number of times, tens of layers of these repetitive units inside of battery cell. So what we thought at the start of the project is, because you have this repetition pattern, then if you put an ultrasonic wave through, and if the frequency is right, then the reflection from these layers will potentially form a resonance, because you have the repetitive, you have the kind of the same pattern reflection overlapping with each other. And so that was the initial idea. And indeed, we found that if you put an ultrasonic transducer at the right frequency, it doesn't depend on how you apply the ultrasonic transducer. You can do a contact measurement, or you can do an immersion setup. And the ultrasound inside of the battery will give you almost exactly the same resonance signal. So if you do a Fourier transform, which gives you a frequency domain component, you can see the frequency components of the reflections inside of the battery cell is almost the same, which means it's from the structure rather than from the transducer. So that gives the resonance frequency of the battery, and it's not only from one type of one pouch cell as well. We've tested a range of pouch cells, and we can always get a resonance signal, even though their resonance frequencies are different. So that's an experimental investigation, but obviously we need to understand how the resonance is forming. So we established from ground up a wave physics model in order to explain the resonance. So you have these metal current connectors inside of the battery, which are the main reflectors of ultrasonic propagation, which goes in this direction. And resonances are essentially phase shifted waves, and their phase differences needs to be 2 pi ahead. So we need to investigate how the phase shifts are happening inside of these layers as well as the electrodes. So the first interesting finding that came out was in order to model the wave propagation through the anode and cathodes, we tried different homogenization methods to calculate the elastic properties. But in the end, we found that if you model anode and cathode similar to slurries, they came up with the physical properties that approximate the wave propagation, the wave speed very well. So that slurry model means that you averaged the bulk modulus of the solid and the liquid parts according to the volumetric weights. So the bulk modulus as well as the density are averaged in that, and they were found out to be approximating the wave speed very closely. I think less than 1% of difference compared to experiments. And also inside of these thin layers, because they are extremely thin, so the low incidence will have local reverberations inside of these batteries, which inside of these metal layers, which also contributed to the phase shift. So by taking up all these phase shift contributing factors, we end up with very simple equations in the end to calculate how the phase shifts are generating these resonances. So the R in the subscript means reflection. So A means aluminium, and C means copper, and E means the electrodes in between. So these are the phase shifts contributing, how they are contributing to the formation of resonances. And also we found that the resonance peaks, in terms of their locations, they are corresponding to the locations of the metal layers, and they can be used to track the position of the metal layers inside of the battery cell. And because aluminium and copper have different elastic constants, so they reflect ultrasound at different amplitudes. So you can use the peak, whether it's stronger or whether it's weaker, to track whether it's a copper layer or whether it's an aluminium layer. So yeah, so that basically allow us to do a range of new investigations and get spatially resolved characterization inside of a battery cell. So that's basically the foundation, the theoretical foundations of how we track, how we use the resonance peaks to track the position of those metal layers and do the spatially resolved characterization. So we've designed a few applications in order to showcase how this could be applied in characterizing a cell. So the first one is we can count how many repetitive units or layers inside of battery cell. So if you give me a new cell without telling me the internal structure, then we can measure how much time it takes for the ultrasound to go through the whole cell, and we can use the resonance to tell how much time it goes through a single layer. So by dividing these two, we can estimate how many layers inside of the battery. So we could came up with a very close lambda. We could also estimate the thicknesses of the anode and cathode, because we know the total thickness of the layer, and we know how much time it's taking the ultrasound to go through these layers, and we know the speed, the wave speed inside of these two. So we can estimate how thick these anode and cathode are. And these are actually corresponding to destructive tests reasonably well. And we have some reason to believe that ultrasound is actually giving better results, because destructive tests, and if you take it apart, then the electrodes are going to expand. The third one is because we can track the position of the copper as well as aluminium layers, and we know the thicknesses of the anode and cathode, then if we do a line scan, if we move the transistor along line, then we can do an image of the cross-section in the thickness direction. So that's what we've done there. And again, because, sorry, I don't know what's happened there. And because we have the capability of tracking the internal internal metal layers from these resonance peaks, then the differences between each peak is giving you the property of a pair of electrodes. So by using that, we're doing SOC, so basically doing the charge and discharging cycling process. And since we can track the copper or aluminum current connectors individually, then we can use that to track the SOC changes in the cycle during the cycling process, and we can change the SOC changes of each individual layers, between an aluminum and the next copper layer, and so on. So we can plot out the change of these individual electrodes during the charge and discharging process. So that's a layer resolved characterization of the SOC during the charge and discharging process. And we found out that towards the center, I think, toward the center, you have a higher changes of the SOC behavior during the charge and discharging process. So that's the capability we've realized and we've accomplished in the publication that we've done last year, and we are actively researching on the in-situ ultrasonic characterizations of a range of properties like thermal gradient. That's because we can now track, as that's also based on the tracking property of the ultrasound for each individual metal layers. And we can also use ultrasonic imaging to detect lithium plating. And also we're characterizing the gassing onset and evolution, especially the gases, starting at very early stage at the sizes of a few microns. I think that at that stage, it's very difficult for even CT to detect because the contrast as well as the size are too small. But ultrasonics have a very interesting behavior regarding gassing, regarding microbubbles, because if you propagate a liquid containing microbubbles at a right frequency, then the frequency that's corresponding to the natural frequency of those bubbles will be completely eliminated due to absorption. So you have a very strong spike of attenuation corresponding to the sizes of microbubbles. So we can use ultrasound to detect the gassing onset at very early stage potentially, and detect that evolution along the way as well. And because we can detect gassing, and at the very early stage of thermal runaway, gassing is starting to happen, then and also thermal gradient as well. So combining these two can potentially provide a very early warning of a potential thermal runaway. And in fact, there are some literatures that's done on thermal runaway warning, and they were using very low frequency through transmission of ultrasound, but we can potentially work on getting a spatially resolved early warning of this happening. And also we are working on the state of health determination using combining the electrical signals as well as the physical interpretation from ultrasound to get a data fused information about the SOH of the batteries. So that's the topics we're actually working on, as I mentioned. And I think that's it from today's presentation. And thank you very much for listening. And I'm happy to take any questions that you might have. Thank you.
Really nice talk. First, I've got two questions. It's really interesting that you can see the variation of the thickness of the electrodes. And if I'm right, you assume certain mechanical properties about the electrodes to calculate certain metrics.
Yeah.
I was just wondering, are you able to get any insights about the interfacial bonding strength between some of the layers? Because sometimes that can be quite important in terms of whether you get delamination from electrodes. So that's my first question.
Yeah, I think it's potentially possible. Delamination and also the internet interfacial bonding is something that ultrasound has been used to characterize, but it will be dependent on the material property and the specific scenario how the delamination is happening. But yeah, I think that's a potentially useful direction that we can research on. But yeah, in general, ultrasonics has been very useful in characterizing interfacial bonding. So that's definitely something that ultrasound can provide insights on.
And my second question, it might be a stupid one in terms of maybe we're orders of magnitude away from it, but is there any impact of the ultrasound measurement on the electrochemistry that's going on?
No, it's basically a slow nanometer scale vibration, and it's not going to, and it's very low amplitude, so it's not going to interfere with the electrochemical changes unless you are doing very high power ultrasound, and which we are also interested in knowing. For example, in the wetting process, ultrasound can be used to drive the liquid movement in porous layers. It has been used to extract oil from sandstone, for example. So if you apply very high power ultrasound, you can drive the liquid movement through a matrix, and we can probably use that to accelerate wetting. But for characterizations, we use very, very low power ultrasound. Ultrasound has been safe for pregnancy tests, so it must be safe for batteries, I would say. Yeah. Do we have any questions from Teams, do you think? Okay.